So another type of related rates problem that I would like to explore is a problem that arises when we are taking three-dimensional containers like cones or cylinders or prisms and filling them with liquid or having liquid leak out of them. So I'm going to show you, before I go through a specific problem with you, I'm just going to show you a little visual here. Again, coming from the GeoGebra applet that I have posted in our course document. And this will just give you a little bit of a visual, hopefully before we start into the problem, of what's actually going on here and what the connection is between some of the dimensions. So right here we have a cone, and we can take this cone and we can fill it with water, or empty the water out of it. So you can see that the water level is increasing and decreasing. And if I take a cross section of that, so if I take the height and the radius, you can see that the cross section actually creates a right angled triangle. And in this particular example that this cone is modeling, the height has a value of 40 and the radius has a value of 20. And you can see here that it creates a right angled triangle with our right angle right here. And what I want you to realize is that as we look at different heights of water, so you can see the blue going up and down, that anywhere I look at a height, the relationship between the height and this radius is going to be similar to the original height and radius of the cone. So here I see that the height here is 2 times the radius, or the radius is 1/2 the height. And no matter how far up or down I go with this height of water, the radius will always be half of it. And that's because we have similar triangles here. So you'll notice in the big triangle that represents kind of the full shape, I have this angle here, which is at the tip. I have a right angle here and an angle here. And no matter where I put my height of water, or how high I make it, it's still going to share this angle here. It still has a 90-degree angle here. So this angle here is always going to be the same as this angle here. So these are similar triangles. So because they're similar, that means that the heights and the radiuses are, the radii are proportional. So the radius here will always be half of the height here. And that's going to be really important as we move forward looking at some of these problems. I'm looking at how the radius and the height are proportional. So what I'm just going to help you visualize here is what happens when we increase the height by a constant rate of change of 1 centimeters per second. So we have dH by dt equals 1 centimeter per second, centimeters per second. And I'm going to click on here so that you can visualize what's going on with the radius. So dr by dt. So if it's going up by 1 centimeters per second for the height, it's going to be increasing by 0.5 centimeters per second for the radius. But I really want your eyes to look down here where it's showing how the actual volume of the water that's in the container is changing with respect to time as the height gets bigger. Okay, so I'm going to start filling this. And like I said, I just want your eyes to look down here to see what's happening to the volume. And as you can see, the volume is increasing. The rate of change of the volume with respect to time is increasing as the height gets higher and higher and higher. And that's because the shape is getting bigger. So what we want to do is we want to be able to predict what the change in the volume with respect to time is going to be for any given height in a case like this. So that is where we will begin looking at a problem. So I'm just going to pull this one up. So here we have, again, the classic leaking or filling container problem. And this particular example is going to be a filling container problem. So we have an inverted conical tank that has water being pumped into it. The tank has a height of 6 meters to start with and a diameter at the top, which is 4 meters across, which means that our radius is going to be 2. We know that the water level is going to be rising at a rate of 20 centimeters per minute. And the height is 2 meters when this is happening. We want to find the rate at which the water is being pumped into the tank. So I'm going to draw myself a picture. I've got my cone. I know that the original height is 6 meters. The original radius is 2 meters. And I'm going to be looking specifically when the height of the water is at 2 meters. So when the H is equal to 2 here. I'm also given the the water level rising at a rate of 20 centimeters per minute. So the water level rising is connected to the height. The height of the liquid is going up. So my dH by dt is going to be 20 centimeters per minute. Identify what we're looking for. Well, we're looking for the rate at which the water is being pumped in. So when we're talking about pumping water in, we're talking about volume. So we're going to be looking, and a rate means we're looking at how the volume is changing with respect to time. So we have dV by dt, and we know that volume is going to be measured in this case because we're given this in centimeters. We'll look at our volume in centimeters cubed, and our time unit is going to be minutes. So we're going to make sure that everything is set up so that we can find the change in the volume with respect to time in centimeters cubed per minute, which means we are going to have to change a few of our dimensions here because the question gives us our height and our radius in meters, and those are our quick fix. We can just take that radius and we can take our height here and we can just change those to centimeters. So that would be 200 centimeters here and 200 centimeters for our radius as well. So what we want to do is we want to start connecting some of these values and dimensions because we want to figure out the rate at which the water is being pumped into the tank. So we're going to be looking at volume. And I will note that down here, I'm going to skip ahead. I'm going to show you the volume for a cone, which is 1/3 pi r squared h. And this is going to be a little bit complicated right now because we have 3 variables, and then life would be a lot easier if we could rewrite this formula with just 2 variables in it instead of 3. So what I'm going to do is I'm going to look at that proportional relationship between the radius and the height and see if I can use that relationship to simplify this formula for me. So over here, just with my given information, well, I know that the height to diameter is 4 to 6, which is 3 to 2. But then I'm not really looking at diameter, I'm looking at the radius because the radius is what's in my formula. So similarly, the height to radius is going to be 6 to 2, which is in lowest terms 3 to 1. And then using this ratio, I can say, okay, well, I know that my height to radius ratio is going to be 3 to 1. And if I cross multiply, I can see that the height is equal to 3 times the radius, or the radius is equal to the height divided by 3. So I can rewrite either one of those variables with respect to each other using the proportionality of the relationship between the height and the radius. So this is going to be handy for us because what we can do now is go back to our volume of a cone formula, and I can rewrite one of my variables in terms of the other. So which one do we want to rewrite? Which one don't we want there anymore? Well, I'm given dH by dt, so this is a value that I'm going to want to use when I'm doing my calculations. So that indicates to me that I want to get rid of my radius, my r. So what I'm going to do is I'm going to take my r, and I know that r is equal to the height divided by 3. So I'm going to replace my r with h over 3. And then I'm just going to simplify this expression. So I end up with the volume is equal to 1 over 27 pi h to the power of 3. So now I have my formula. It's simplified. It's written with respect to 2 variables instead of 3. And now I'm going to take the derivative with respect to time of both sides. So d by dt of v and d by dt of 1 over 27 pi h cubed. Well, I know that the derivative of v is just 1. So I have 1. And then I'm going to tag on the derivative of v with respect to t, so dv by dt. And I know that's going to be equal to the derivative of this. Well, 1 over 27 pi is just a constant, and the derivative of h cubed is 3h squared. So I have 1 over 27 pi 3h squared, and then I'm going to tag on dh by dt from my implicit differentiation. And when I simplify that, I get the derivative of v with respect to t is equal to 1/9 pi h squared times dh by dt. So here's my nicely written formula for dv by dt. And at this point, I can just sub in the values that I found above. So I know that h squared as in centimeters, because I want to make sure that my units are matched up, is going to be 200 centimeters. I'm going to square that. And then I'm going to times that by dH by dt, which is 20 centimeters per minute. And when I calculate this out, I get 800,000 pi over 9 centimeters cubed per minute. And it's positive. I forgot to mention at the very beginning that I considered the positive value to be rising or filling, and a negative value to be getting lower or falling. So it makes sense that my volume is changing with respect of time by rising, by getting higher, by getting bigger. And I can say that the water is rising or being pumped in at a rate of 800,000 pi over 9 centimeters cubed per minute.